Hello everyone, welcome to today's presentation. I'm excited to have you here. Today, we'll be exploring the D and F block elements. This will include an overview of their properties and significance in chemistry. So, let's get started and dive into this fascinating topic. All right, let's take a closer look at the F block or inner transition elements. These are a special set of elements that are often referred to as the lanthanides and actinides. They sit below the main body of the periodic table, which is why we call them the F block. These elements are unique because they involve the filling of the 4f and 5f orbitals, which gives them some interesting properties. Now, just above these F block elements, we have the D block elements. These are what we typically think of as the transition metals, like iron, copper, and gold. They are characterized by the filling of the d orbitals, and they tend to be highly versatile, often used in construction, electronics, and many industrial applications. Connecting these points, it's important to recognize that the F block elements are a bit more complex due to their electron configurations, which influence their chemical behavior and physical properties. While the D block elements are more familiar and well-studied, the F block elements have some of the most interesting and unique chemistry in the periodic table. So, understanding these blocks helps us see the bigger picture of how elements are organized and why they behave the way they do, especially in terms of their electron configurations and the resulting properties. This overall theme of structure and behavior is central to grasping the periodic table's design and its predictive power. Let's take a closer look at the D block elements. These are often called the transition metals, and they occupy a special position in the periodic table. They are characterized by having partially filled d orbitals, which give them some unique properties. For instance, many of these elements are known for their ability to form colorful compounds and to exhibit multiple oxidation states. This flexibility in oxidation states is what makes them so versatile in various chemical reactions and industrial applications. Additionally, the D block elements are essential in everyday life. Think about the use of iron in construction or the role of copper and nickel in electrical wiring. Their properties, such as high melting points and good conductivity, make them invaluable. As we progress through the presentation, keep in mind that these elements are not just interesting from a scientific perspective, but also crucial to modern technology and industry. Their unique electronic configurations and chemical behaviors are what set them apart from other elements on the table. Originally, the name transition metals was derived from the fact that their chemical properties are transitional between those of S and P block elements. This means that these metals exhibit characteristics that are somewhere in between, making them quite unique. There are mainly 4 series of the transition metals, which are generally also called transition elements. These elements are placed in 4 long periods, period 4, 5, 6, and 7, indicating their position in the periodic table. As you move across these periods, the d orbitals are progressively filled, which is a key point because the filling of d orbitals influences their properties significantly. The elements of groups 3 through 12 fall into this category, and they are collectively known as the D block elements. So, understanding these key points helps us see how their electronic structure and placement in the periodic table define their unique chemical behavior. Let's start by looking at some examples of transition metals. These include various precious metals like silver, gold, and platinum, as well as metals that are industrially important such as iron, copper, and titanium. These metals all belong to the transition metals series. Now, since silver, gold, and platinum are at the ends of the 3D, 4D, and 5D transition series, respectively, their chemistry is studied along with the chemistry of the other transition metals. It's also important to understand that not all metals with d electrons are classified as transition metals. For instance, zinc, cadmium, and mercury, which are part of group 12, have a full D10 configuration in their ground state and in most common oxidation states. Because of this, they are generally not regarded as transition metals. According to IUPAC, the key defining feature of transition metals is that they have an incomplete D subshell either in their neutral form or in their ions. This incomplete D subshell is what gives these metals their unique chemical properties. So, in summary, transition elements or transition metals are characterized by this incomplete d-electron configuration, which plays a crucial role in their chemistry and reactivity. This concept ties back to our overall theme of understanding the diverse properties of different metal series. Let's look at some specific examples to understand this better. For instance, chromium, which has an atomic number of 24, has a configuration of 3d541 instead of the expected 3d442. Similarly, copper, with Z equals 29, exhibits a configuration of 3d1041 rather than 3d942. What this tells us is that configurations with half-filled or fully filled sets of orbitals tend to be more stable. These configurations are energetically more favorable. However, there are exceptions to this general trend. These exceptions occur because the energy difference between the n1d orbitals, which are the inner d orbitals or penultimate shell, and the outermost ns orbital is very small. So, in most cases, the electronic configuration of the outer orbitals of these elements follows the pattern of n1, d1 to 10, and n, 1 to 2. This means that the electrons tend to fill these orbitals in a way that balances stability and energy considerations. Understanding these configurations is crucial because they influence the chemical behavior and properties of the transition metals in the D block, which is central to our overall discussion on their chemistry. The high melting points of these metals are primarily due to the involvement of a greater number of electrons from the n1d orbitals, in addition to the ns electrons, during interatomic metallic bonding. This means that more electrons participate in holding the atoms together, which requires more energy to break these bonds. As a result, their melting and boiling points tend to be high. Transition metals are also very hard and tend to have low volatility, meaning they don't easily vaporize at room temperature. This hardness is linked to the strong metallic bonds formed by the many electrons involved. Nearly all transition elements display typical metallic properties. They have high tensile strength, making them resistant to breaking under tension. They are ductile and malleable, so they can be drawn into wires or hammered into sheets without breaking. Additionally, they exhibit high thermal and electrical conductivity, which makes them useful in electrical applications. And of course, they have a metallic luster, giving them that shiny, reflective appearance we associate with metals. In summary, these physical properties highlight the strength, stability, and utility of transition metals, connecting back to their unique electronic structure and bonding characteristics. Let's take a closer look at the melting points of transition metals. As we see, there is a notable dip in melting point at manganese. This can be explained by its stable half-filled d subshell, which means the electrons are held more tightly. Because of this, there's less delocalization of electrons, leading to weaker metallic bonds. Now, as we move across the series, the number of unpaired d electrons increases up to the middle of the period. This increase actually enhances the metallic bonding, so the metallic strength and consequently the melting points tend to increase as we approach the middle. However, an interesting pattern emerges in any row. The melting points generally rise to a maximum at D5. But here's the catch: manganese and technetium are exceptions, showing anomalous values. After reaching that maximum, the melting points tend to fall off regularly as the atomic number increases further. So, in summary, the melting points of transition metals are influenced by the electron configuration, particularly the number of unpaired d electrons, which directly affects the strength of metallic bonding. In general, the more valence electrons an atom has, the stronger the bonding tends to be. This is because additional valence electrons can participate in bonding, leading to more stable and stronger interactions. You'll notice that there are maxima around the middle of each series, which suggests that having one unpaired electron in each d orbital is especially favorable for strong interatomic interactions. This unpaired electron can enhance bonding strength because it allows for more effective overlap between orbitals. These elements with maximum bonding strength also tend to have high enthalpies of atomization. That means it takes a lot of energy to break them down into individual atoms, which is another sign of the strength of their bonds. So, in summary, the number of valence electrons plays a crucial role in bonding strength, and the presence of unpaired electrons in the d orbitals makes a significant difference in how strongly atoms interact. This connects directly to our overall theme of understanding the factors that influence atomic and molecular stability. Let's talk about how atomic size varies within the 3D series. First, an increase in electron-electron repulsion tends to make the atom larger because the electrons are pushing each other apart. But at the same time, an increase in the effective nuclear charge pulls the electrons in closer, which decreases the size. These two effects work against each other, so the variation within a series is actually quite small and not perfectly systematic. Now, a key reason for this is that d orbitals provide poor shielding. This means that the outer electrons don't effectively block the nuclear attraction, so the net electrostatic attraction between the nucleus and the outermost electrons actually increases. As a result, the atomic radius tends to decrease as you go across the series. This trend is also reflected in the ionic radii of these elements. Generally, in the 3D series, as the atomic number increases, the atomic radii gradually decrease. So overall, while there are some fluctuations, the general pattern is a decreasing size with increasing atomic number in the transition metals. The net result of the lanthanoid contraction is that the second and third D series, such as zirconium with a radius of 160 picometers and hafnium with 159 picometers, actually have very similar atomic sizes. This leads to them having quite similar physical and chemical properties. Now, this happens because the filling of the 4f orbitals before the 5d orbitals causes a steady decrease in atomic radii, which is known as the lanthanoid contraction. It occurs due to the imperfect shielding effect of the 4f electrons. They don't shield the nuclear charge as effectively as other electrons might. You might notice that from the first transition series, the 3d series, to the second, the 4d series, there's an increase in radii. But then, surprisingly, the radii of the third series, the 5d elements, are almost identical to those of the second series. This is a direct consequence of the lanthanoid contraction, which compresses the sizes of these atoms despite the addition of more electrons. So overall, when we look at atomic radii across transition elements, this contraction explains why the sizes don't increase as much as we'd expect when moving to higher atomic numbers in the 5d series. It's a key concept that influences many properties of these elements, connecting the structure to their behavior. Let's look at the ionization enthalpies of some transition elements. First, for iron and manganese, we see that iron has a lower first ionization energy compared to manganese. This is because Fe has the electron configuration 3d6, while Mn is 3d5. So removing an electron from Fe is slightly easier than from Mn, due to the different electronic configurations. Now, moving on to the second ionization energies of vanadium, chromium, nickel, copper, and zinc, we notice some interesting trends. For vanadium and chromium, the ionization energy increases from V to Cr, since chromium has a 3d5 configuration, which is more stable and thus requires more energy to remove an electron. Conversely, for nickel, copper, and zinc, we see that copper has a higher ionization energy than nickel, because copper has a filled 3d10 shell, making it more stable and harder to ionize. Zinc, with its filled 3d10 configuration, has the highest ionization energy among these. Generally, across each series of transition elements, from left to right, there is an increase in ionization enthalpy. This trend occurs because as we move across the period, the nuclear charge increases. This stronger positive charge pulls the electrons more tightly, making it harder to remove an electron. Additionally, as the inner d orbitals fill up, they shield the outer electrons less effectively, further contributing to this increase. So, in summary, the key point here is that ionization enthalpy increases across a series of transition elements from left to right, mainly due to the increasing nuclear charge and the way electrons are arranged in the d orbitals. This trend is fundamental to understanding the chemical reactivity and properties of these elements. Let's take a closer look at oxidation states across the series. You'll notice that at the extreme ends of the series, the number of oxidation states tends to be lower. This is because these elements either have too few electrons to lose or share, like scandium and titanium, or they have many d electrons, which means fewer orbitals are available for sharing electrons when aiming for higher valency, as seen in copper and zinc. In contrast, the elements that show the greatest number of oxidation states are usually located near the middle of the series. This middle region provides a greater variety of oxidation states, leading to what we call variable oxidation states. This variability is quite significant because it reflects the complex chemistry of these elements. It also ties into our overall theme of how electronic structure influences chemical behavior. Understanding where these extremes and the middle lie helps us predict and explain the different oxidation states an element can exhibit. Let's talk about the variability of oxidation states, which is a characteristic feature of transition elements. This variability arises from the incomplete filling of their d orbitals. Because of this, their oxidation states tend to differ from each other by 1 unit. For example, you might see oxidation states like +7, +8, +9, or +10, which are close in value. This is quite different from non-transition elements, where the oxidation states usually differ by 2 units. This difference is mainly due to the inert pair effect, which stabilizes certain oxidation states in non-transition elements. Now, when we consider electrode potential values, these depend on several factors. Key among them are the enthalpy of sublimation of the metal, the ionization enthalpy, and the hydration enthalpy. These factors influence how easily a metal can lose or gain electrons in various conditions. In solution, however, the stability of compounds doesn't just depend on ionization enthalpies. Instead, it's primarily governed by electrode potentials. These potentials give us a measure of how stable a particular oxidation state is within the environment of an aqueous solution. So, in summary, the stability of oxidation states in transition metals is closely linked to their electronic configuration, and understanding electrode potentials helps us predict which states are more stable under specific conditions. This concept ties into the overall theme of how transition elements behave chemically and electrically. Let's take a closer look at the trends in M3 plus M2 plus standard electrode potentials. The relatively higher value for vanadium, V, is interesting because it relates to the stability of the V2 plus ion, which has a half-filled T2G level. This stability makes the V2 plus state more favorable, reflected in the higher potential. Moving on to manganese, Mn. Its high potential indicates that Mn2 plus with a D5 configuration is particularly stable. The D5 configuration is symmetric and half-filled, which lends extra stability to that oxidation state. In contrast, iron shows a lower potential, but that actually points to the extra stability of Fe3+ with a D5 configuration. So, even though Fe2+ isn't as stable, Fe3+ benefits from a stable half-filled D5 state, which influences its electrode potential. Now, zinc stands out with the highest value among these metals. That's because removing an electron from Zn2+ means going from a full D10 configuration, which is very stable, to a less stable state. The stability of the D10 configuration explains the high potential for zinc. Let's also look at scandium. Its low potential is due to the stability of Sc3+, which has achieved a noble gas electron configuration. This stability makes it less likely to be reduced back to Sc2+ or Sc. Finally, when we consider the trends in M2 plus M and M3 plus M2 plus electrode potentials, we're essentially examining how stable these different oxidation states are and how easily they can be interconverted. These stability patterns are crucial for understanding the behavior of these metals in various redox reactions and applications. Let's look at the key points from this slide. First, we see that Pt in the +4 oxidation state is more easily attained compared to Ni. This means that platinum can reach the +4 state more readily, while nickel requires more energy to do so. As a result, Pt IV compounds tend to be more stable than Ni IV compounds. Now, considering their common oxidation states, nickel typically shows a +2 state, whereas platinum usually shows a +4 state. This difference is linked to their ionization energies. If we examine the sums of their first and second ionization enthalpies versus the third and fourth, we notice that for nickel, IE1 plus IE2 is 2.49 kJ-mol1, and IE3 plus IE4 is 8.8 kJ-mol1. For platinum, these values are 2.66 kJ-mol1 and 6.7 kJ-mol1, respectively. What does this tell us? Well, the smaller jumps in ionization energies for platinum indicate that removing electrons to reach the +4 state is relatively easier for platinum than for nickel. This explains why platinum more readily forms +4 compounds, while nickel favors the +2 state. In summary, the lower energy requirement for platinum to attain the +4 state makes its compounds more stable and more likely to exist in that oxidation state compared to nickel. This insight helps us understand their chemical behavior and stability in various chemical environments. Let's start with the solution. Scandium, which has the atomic number 21, does not exhibit variable oxidation states. Now, can anyone think of a transition element that also doesn't show variable oxidation states? That's right, many of the earlier transition elements tend to have a fixed oxidation state. Moving on, let's understand the nature of transition metal oxides. Oxides of transition metals in lower oxidation states are generally ionic and basic. This means they tend to react with acids to form salts and are quite soluble in water. On the other hand, when these metals are in higher oxidation states, they tend to form covalent oxides that are acidic. So the key difference here is in the type of bonding and acidity. Now, why does this difference occur? It relates to the nature of the metal-oxygen bond. In lower oxidation states, the bonds are more ionic, leading to basic oxides. In higher oxidation states, the bonds become more covalent, resulting in acidic oxides. This shift is due to the increased positive charge on the metal, which pulls the oxygen atoms closer and shares electrons more covalently. Next, let's look at chromium ions. Plus is more stable in aqueous solution than Cr2+. The reason is that Cr3+ has a higher hydration enthalpy. This is because Cr3+ has a smaller ionic radius and a higher charge, which increases its attraction to water molecules, making it more stable when dissolved. Finally, between Cr2+ and Cr3+, which one is more stable in water? The answer is Cr3+. Its higher charge and smaller size mean it interacts more strongly with water molecules, leading to greater stability in aqueous solution. So, in summary, understanding how oxidation states influence the bonding and stability of transition metal oxides and ions helps us grasp their chemical behavior much better. Let's take a closer look at the F block, also known as the inner transition elements. These elements are quite fascinating because they sit separately from the main body of the periodic table, nestled in the lanthanide and actinide series. They are called inner transition because they transition between the main groups, but their unique electron configurations set them apart. What makes these elements especially important is their electron structure, specifically their f orbitals. These orbitals are being filled as we move across the series, which influences their properties and reactivity. For example, many of these elements are used in advanced technologies. Think of the lanthanides in magnets and phosphors, and the actinides like uranium in nuclear energy. Understanding the F block helps us see how electron configurations influence chemical behavior, and it ties into our overall theme of how atomic structure governs properties. Recognizing these elements' roles in modern applications underscores their significance beyond just the periodic table. Let's talk about the F inner transition metals, specifically those from 90th to 103 Lr. These are known as actinoids because they come immediately after actinium in the periodic table. Now, when we discuss the actinoids, we're not just talking about these 14 elements. We also include actinium itself, which has the symbol AC. It's interesting to note that lanthanum, La, closely resembles the lanthanoids, so it's often included in discussions about the lanthanide series. For simplicity, many refer to the lanthanoids collectively using the symbol Ln. Moving on to the lanthanoids, these are the 14 elements from 58C to 71 Lu. They're called lanthanoids because they come immediately after lanthanum in the periodic table. Now, a key point about these inner transition metals is their general electronic configuration. They typically have a configuration that can be represented as N2F014, meaning the f orbitals are filled with up to 14 electrons, and N1D01, indicating that one or no electrons are in the d orbitals, along with the outermost ns2 electrons. The defining characteristic of these elements is that their last electron enters the N2F orbitals. That's why we call them inner transition elements. They're filling the inner f orbitals, which are beneath the main part of the periodic table. In summary, the F-block elements include both the lanthanoids and actinoids, and understanding their electronic configurations helps explain their unique chemical properties and their placement in the periodic table. The decrease in atomic radii across the lanthanoids is not as uniform as it is in M3+ ions. Instead, what we observe is a gradual decrease in size, and this phenomenon is known as the lanthanoid contraction. This contraction results in a steady increase in the nuclear attraction exerted on the outer electrons. One of the key reasons behind this is that the 4f electrons are largely ineffective at shielding the outer electrons from the increasing nuclear charge. Because of this poor shielding, the outer electrons feel a stronger pull from the nucleus as the atomic number goes up. As we move across the lanthanoid series, each new element has one additional electron in the 4f orbital and one more proton in the nucleus. This incremental addition intensifies the electrostatic attraction, which explains why atomic and ionic sizes gradually decrease across the series. Understanding this size reduction and the concept of lanthanoid contraction is important because it influences the chemical behavior and properties of these elements, connecting back to the broader theme of atomic structure and periodic trends. Let's begin by discussing the concept of lanthanoid contraction. This phenomenon occurs because of the poor shielding effect of f electrons, which results in a gradual decrease in the atomic and ionic sizes of lanthanoids as the atomic number increases. Essentially, as we move across the lanthanoid series, the electrons are pulled closer to the nucleus, leading to smaller atomic radii. Now, this contraction has some important consequences. For example, it causes a close resemblance between the properties of 4D and 5D transition series, making elements in these series quite similar in behavior. Additionally, because of the lanthanoid contraction, the radii of zirconium, Zr, and hafnium, Hf, are almost identical, at 160 pm and 159 pm respectively, which makes their separation quite difficult. Another key point is that the ionization enthalpy of the 5D transition series is higher than that of the 3D and 4D series. This means that it requires more energy to remove electrons from 5D elements, reflecting their increased nuclear attraction due to contraction. Furthermore, there's an increase in the covalent character of the M-O bond across the series, which results in a decrease in basicity from left to right. Lastly, it's important to note that the lanthanoid contraction causes the sizes of the lanthanoid ions, M3+, to decrease as their atomic number increases, which affects their chemical behavior and how they interact with other elements. So, in summary, lanthanoid contraction is a key concept that influences many properties of these elements and their compounds, and understanding it helps explain the similarities and differences we observe across the series. Let's talk about the oxidation states of lanthanoids. The most stable oxidation state for these elements is +3. Because of this, ions in a +2 oxidation state tend to be oxidized to +3 by losing electrons, which makes them good reducing agents. Conversely, ions in a +4 oxidation state tend to gain an electron and reduce to +3, so they act as good oxidizing agents in aqueous solutions. Now, why are ions like Sm2+, Eu2+, and Ib2+ in solution good reducing agents? Well, their electronic configurations are quite telling. For example, Eu2+ has an F7 configuration, Ib2+ has an F14 configuration, and C4+ has a noble gas configuration. These configurations influence their tendencies to either lose or gain electrons. Occasionally, ions in +2 and +4 oxidation states can be obtained either in solution or as part of solid compounds, but the predominant and most stable oxidation state for lanthanoids remains +3. In summary, understanding these oxidation states helps us predict chemical behavior, whether an element will act as a reducing or oxidizing agent, and gives us insight into their stability and reactivity in different environments.